Hello and welcome to another WJEC A level physics question. This was from the May 2011 Unit 1 and it is question 4 on that paper, and it's basically sort of equations of motion, if you like, what some people call the Suvat type equations. To start with, we've got a velocity time graph given for a body which is accelerating in a straight line, and we can see that this object has started at a velocity of u and reached the velocity of v after a time t. Using symbols on the graph, we've got to write down an expression for the gradient and state what it represents. Well, the gradient is the acceleration. That's simple learning. And the gradient is the change in y, which will be v minus u. So imagine a dotted line across here. That side is v minus u over t. Next, we're asked to write down an expression for the area under the graph and state what it represents. Well, the area under a velocity time graph is displacement. And there's various equations we could use here. We could split it up into a rectangle and a triangle as we've got on the diagram, but let's just do it as a trapezium. And the area of a trapezium is half the sum of the parallel sides. The two parallel sides are u and v, times by the distance in between, which is t, and you might recognize that as one of the Suvat equations. Now next we have to show clearly, using the usual symbols, that x equals ut plus a half at squared. Well, what we'll notice is that in this equation that we're trying to get, there is no letter v, so what we're going to do is we're going to rearrange acceleration is v minus u over t from the first question into the form where v is equal to u plus at. I'll just put it in brackets there, that's from part 1. Then we're going to substitute that into the equation that we've got in part 2. So in part 2 we had x equals a half u plus v times t. We're going to replace the v by u plus at. And if we look at that, we simply got x equals, well, u plus u. Oh, sorry, slight mistake on the last bit. We've got to forget the t at the end of the bracket there. So if we look at this expression carefully, we've got inside the brackets u plus u is 2u, half of 2u is u times t, that's where the ut bit comes from, and at times t is at squared, but the half at the front gives us the half at squared. Next we're given some information about a cyclist who accelerates from rest with a constant acceleration of 0.5 meters per second squared for 12 seconds. And we've got to calculate the distance travelled in this time. Now I'd like my students to think carefully about what motion they're looking at, and here is obviously the motion from the start. And always to choose a direction to be positive. Well, there's only one sort of direction that the cyclist is moving, which is forwards. And then I'd like them to write down the 5 letters that we use to represent quantities in the equations of motion. Fill in what they know. So for example here we know that u is 0. I like them to put units on as well, just in case the question gives us something like centimeters instead. The acceleration is 0.5 meters per second squared. The time is 12 seconds. And both x and v are unknowns. But for the first part of the question, we're trying to find x, so we're going to choose the equation that hasn't got v in, which just so happens to be the equation that we just derived. So x equals ut plus a half at squared. We're trying to find x, so there's no rearrangement needed. U is 0, so the ut term becomes 0. So we're just left with a half times 0.5 times 12 squared. Now 12 squared is 144, half of that is 72, and half it again is 36. So our answer is 36 meters. To find the maximum velocity attained, well, we can use any equation with v in. Let's use the simplest one. V equals u plus at. So 0 plus 0.5 times 12, and 0.5 times 12 is 6. So we got 6 meters per second. Next, after 12 seconds, the cyclist stops pedaling and freewheels to a standstill with a constant deceleration over a distance of 120 meters. So this time it's a different set of information. I'm still going to stick with the forward direction as being positive, but I'm going to rewrite what I know about each of the Suvat letters. So we know in this case that u is the 6 meters per second that we worked out in the previous part of the question. The cyclist gets to a standstill, so the final velocity is 0. The distance is 120 meters, and here both a and t are unknowns. In the first part of the question, we're trying to find the time, so we're going to use the equation that hasn't got acceleration in, which is x equals a half u plus v times t. Now here the v is 0, so that simplifies to x equals a half ut. We're trying to find the time, so a quick rearrangement of that will give us 2x over u. So we have 2 times 120 divided by 6. 6 goes into 120 20 times. 2 times 20 is 40 seconds. To find the acceleration or the deceleration of the cyclist, we can just use the definition of acceleration, which is a rearrangement of v equals u plus at again. So v is 0, u was 6, and t was 40 seconds. We could use any of the other equations. That's not a problem at all. Note that we get a negative sign with the answer here. The exam board won't be too worried about whether or not you've got the minus sign in because they've asked for a deceleration. So put the numbers into the calculator or whatever, and we get minus 0.15 meters per second squared. Okay, so next the question asks us to draw an acceleration time graph on the grid below for the whole of the cyclist journey. So I've pre-drawn this. Let's look at how we would have set this out. So first of all, the acceleration goes from 0.5 at the start for the first 12 seconds, and for the last 40 seconds, in other words up to a total time of 52 seconds, the acceleration is minus 0.15. So we needed an acceleration scale to cover everything from roughly minus 0.2 up to plus 0.6 with labels with units. The time scale had to go past 52 seconds, so the obvious scale was to go across in seconds, and again axis labelled with units as well as the quantity of time. The question then continues. It says, in reality, the cyclist would not slow down with constant deceleration, and this is because the total resistive force acting on the cyclist consists of a constant frictional force of 8 newtons and an air resistance force, which is proportional to the square of the cyclist's velocity. When the cyclist was travelling with maximum velocity, the total resistive force was 165 newtons, and we've got to calculate the force of air resistance at that velocity. Well, that's simply just a matter of taking the 8 newtons constant frictional force away from 165, which gives us 157 newtons. Then we've got to find the total resistive force acting on the cyclist when it's moving at half the maximum velocity. Well, here the important bit is the proportionality to the square of the cyclist's velocity. So if we halve the cyclist's velocity, it means that the air resistance force isn't going to just divide by 2, it's going to divide by 2 squared, or 4. So the first step is to simply divide the air resistance force by 4. I'm not going to bother working that out. The total resistive force would then be that answer plus the 8 newtons constant frictional force that we've got there. So 157 divided by 4 gives us 39.25, plus the 8 will give us an answer of 47.25 newtons. So once again, thank you very much for listening. Please remember to like and subscribe.